We're going to talk today about solving exponential and logarithmic equations, actually solving for x. I know we've done some examples when we were exploring exponential functions and logarithmic functions, but now we're just going to concentrate on solving for an unknown variable, either in an exponential function or in a logarithmic function. So let's take a look at some examples. Here is an example where, and we've done this before, this is just a reminder, if we can manage to get the same base on either side of the equal sign, then we know that we can, in essence, drop the base. What we're doing is taking the logarithm of that same base on both sides. But we, in essence, get to drop the base and just set the exponents equal to each other and solve for the variable. So that's an equation that we're comfortable with, and we've been doing this for quite a while. Here's another example. We make sure that we have the same base on both sides. We write whatever base that we're initially given in terms of probably a pretty small value. 3 cubed is 27, 3 squared is 9. So when we raise a power to a power, we multiply. And once we get those two exponents, those two exponential expressions into a form where we just have bases equal to one another, we can drop the bases and then again solve for the variable. So these examples we're really comfortable with, nothing much new here. We've solved a few rudimentary, really simple logarithmic functions like this one by basically taking it and changing the logarithm into its equivalent exponential form. We know if we take the base to this value out here and set it equal to the antilog or the expression, then we can solve for the variable. So log base 3 of x equals 2 can be rewritten as 3 to the 2 raised to the x power. Well, 3 squared is 9, so x equals 9. The same thing here, if we have a base of x, we raise it to a power of 2, set it equal to 16, and solve for x. And I would make a note on this example, it should be algebraically that x could equal positive or negative 4, but remember, because x is the base of a logarithm, all of those bases have to be positive. So that's why they say that x squared equals 16 is only positive 4. Here we have the log of 1000. We know we have an assumed base here of 10. So log base 10 of 1000 equals x. 10 to the x would equal 1000, and therefore x would equal 3. So again, pretty straightforward way to solve logarithms, simply by putting them into their equivalent exponential form, and we know how to solve exponential functions. So if the exponent's a variable, take the natural log of both sides of the equation and use the appropriate property. This is another way to solve for the variable. This is a technique that we haven't used before. We've always been able to maneuver on both sides of the equal sign to get the same base so that we could just drop the bases and set the expressions equal. But we do have exponential functions where that's not the case. There's no way here for me to write 7 equivalently as an exponential expression with a base of 2. But I can, again, do the same operation on both sides of the equal sign, and I can get x out of being in the exponent position by using that logarithmic rule that says the power gets to pop down front. And I know the natural log of 2 and the natural log of 7 may put you off a little bit, but those are real numbers. There's no variable in the natural log of 7. There's no variable in the natural log of 2. So now we're just going to go about solving for x. This is x times the natural log of 2. So we're going to divide both sides by the natural log of 2. And this is a perfectly fine answer. This is a real number. It's an exact real number. You do not have to pick up your calculator and find a decimal approximation. But if you do, if you want to, make sure you give those answers accurate to 3 decimal places. You just put natural log of 7 in your calculator and then divide that by natural log of 2, and you'll get 2.807. This is a technique that we'll be using often. So remember, you can introduce natural log. You can reduce log-based anything on both sides, but we like to introduce something that we can use our calculator easily with log base 10 or log base e. I want you to get comfortable with log base e, or the natural log, because it's going to be what you're going to be using a lot in calculus. So we're just going to exclusively introduce the natural log to both sides. So here's another example. E to the x equals 72. There's no way for me to write 72 as an exponential expression that has a base of e. So there's my clue that I'm going to have to introduce natural log on both sides. Well, natural log of e to the x is just x, because natural log of x and e to the x are inverse functions and they undo each other. So all that leaves me with was the initial input value. I put x into the e function, I put e to the x into the natural log function, and it mapped me back to where I started. Since they're inverses, it just leaves me with that initial domain input value that I had, and here we can see it was x. So again, natural log of 72 is a perfectly good number. Nothing wrong with it at all, but you can put it in your calculator and you will get 4.277. Again, all answers must be accurate to 3 decimal places. Here's another one that's a two-step problem. We have 2 terms on one side and 1 term on the other, so we have to do a little algebra to clean it up. We're going to have to subtract 8 from both sides. We're going to have to divide both sides by 2. And then we're back in the position that we were on the previous example, where we realize there's no way to write 6 as an exponential expression that has a base of e, so we're going to have to introduce natural log on both sides, which is great because the natural log of e to the x allows us just to wind up with x. So again, always accurate to 3 decimal places. Here's another example. This is not one where we can introduce natural log. This is just a simple, straightforward logarithmic expression, but we can go back and put the base to this exponent and set it equal to the antilog and then solve for the variable. So we're going to have a mixture of these techniques in everything that we're doing. So you're going to have to pay attention to which technique you want to use. So this says solve 3 times the natural log of the expression 2x equals 12. So we divide both sides by 3. We get the natural log of 2x equals 4. Now we want to undo natural log. Before we wanted to undo or take care of the fact that we had e. Well, we're going to use the fact that natural log is log based e, and that if I put that into the e function machine, it's going to undo the natural log part of what's going on here. So e raised to the natural log of 2x is where they get 2x from, right here. But if I raise what's on the left-hand side and put it as an exponent to a base of e, I've got to raise what's on the right-hand side and make it the exponent to a base of e. And then we just take e to the 4th, our calculator can do that for us, and divide by 2, we get 27.299. You do want to take a minute and make sure that your results are valid for your function. If you get a negative input value or a negative x value, for instance here, if we had gotten a negative value, we started with a logarithmic function, we know that logarithms will never have a negative input value. So your answer has to make sense in the context of the function that you're working with. So just pay attention to that, make sure you understand that. We can also use logarithmic properties. We've already used that one exponential property, but we have the product and the quotient properties we can use as well if we need to. If we can collapse things down, condense both sides, clean things up, and then figure out what we need to do as far as inverse operations to actually solve for our variable that we're after. For instance, here's one, log base 3 of 6 equals log base 3 of 3 plus log base 3 of x. So we're going to use that logarithmic property that says if I have the sum of 2 logarithms to the same base, I can condense that down into one logarithm of that same base and multiply the expressions. Here we have log base 3 on both sides, so we can introduce a base of 3 for the exponent on both sides. In essence, what it looks like is we just get to drop the logarithms and set the expressions equal to each other and solve for our variable. So these are not terribly difficult to do. You just have to make a decision on what it is you're going to do, whether you're going to use a logarithmic rule, whether you're going to change a logarithm into its exponential equivalent, whether you're going to introduce natural logs on both sides. You have to look at the setup of your problem and make a decision on which of those techniques you're going to use to actually solve for the variable. That's the most challenging part of these types of problems. So here we have log base 10 of 16 equals x times log base 10 of 2. Well, because of this x, we can't just drop both of the logarithms. We can only do that if there's nothing else being multiplied there. Well, we can use that property that allows us to pop this coefficient, this product, this factor, up and make it the exponent of this expression. So now we have log base 10 of 16 equals log base 10 of 2 to the x. Now we get to use those inverse operations or drop the logarithms and set the expressions equal to each other and solve for x. This is 2 to the x, by the way. I know it looks like, okay, there it is. So 2 to the x, and 16 can be written as 2 to the 4th, therefore x will be 4. All right, another example, 1/3 log base 4 of x equals log base 4 of 4. Again, just like the x gave us a problem in the last equation, the 1/3 is what gives us a problem here, because it's not 1 to 1. This is 1/3, that's got a coefficient of 1, so we're going to use that property again and just pop that up and make it the exponent of x. Then we get to set the expressions equal to each other and solve for x. So pretty straightforward. Here's one where we're going to have to do several things. We're going to have to use a lot of those log properties to condense this down where we can actually get things set equal to each other. So here I have 7x log base 2 of 5 equals 3x log base 2 of 5 plus 1/2 log base 2 of 25. So I can pop the 7x up and make it the exponent of 5. I can pop the 3x up and make it the exponent of 5. And then I recognize that 25 is 5 squared. I can pop the 1/2 up there, and so the square root of 25 or the square root of 5 squared is just going to leave us with 5. Now there is a property here where we could actually put these two together. So we could multiply these two together. The step is not shown here, but what we would get on the right is log base 2 of 5 to the 3x plus 1. Right, because we would multiply those expressions, 5 to the 3x times 5 to the 1. And when we multiply the same bases, we add the exponents. That's how they just dropped everything and said what's going on the right-hand side is 3x plus 1. So gather like terms and solve for x. So one last example. Again, we're going to use logarithmic rules, collapse everything down. Here we get to multiply 7 times 2. Here we get to multiply x times 5 minus x because of those product properties of the logarithm. We have log base 7 on both sides of the equal sign, so we get to drop that and set our expressions equal to each other. This is an exponential, this is a quadratic expression, so we know how we solve those. We factor and then set each factor equal to 0. Again, going back to the warning that I gave you earlier, you have to make sure that your answers work in the context of the expression you're working with. We're talking about input values to logarithms here. We don't have any domain values in a logarithm that are negative. So the only answer that's going to work for us here is x equals 2. Even though the algebra would tell us that negative 7/5 is a choice for x, it's not in the context of this problem. So there's several problems that we've done, several techniques to solve these kinds of equations. Come to class next time and we'll do some practice on logarithmic and exponential equations.